Imagine waking up tomorrow and discovering that yesterday hasn't happened yet. That the future has already occurred, but the present is still catching up. Absurd? Perhaps not. What if everything you have been taught about time, that it flows like a river, always forward, never backward, is fundamentally incomplete? In a laboratory beneath Stanford University in 2019, physicist Barbara Chen observed something peculiar. A quantum particle appeared to respond to a measurement before the measurement was made. The equipment readings made no sense until she realized causality itself was in question. The effect preceded its cause by 3.7 microseconds. "I checked the equipment 27 times," she later recalled in her journal. "I was certain we had a calibration error, but the data remained consistent across 300 trials. Something was happening that violated everything we understand about temporal sequence." Her discovery was quietly filed away, too controversial, too paradigm-shattering to publish without overwhelming evidence. Yet it joined a growing collection of anomalies that scientists across disciplines have been documenting for decades. Anomalies that suggest time may not be what we think it is. That behind the simple forward march of seconds, minutes, and years lies a far more complex reality. A hidden architecture of time that our textbooks never mention and our teachers never explain. This is not science fiction. This is the frontier of physics, neuroscience, and mathematics, where researchers are uncovering evidence that time may branch, loop, and even fragment. That simultaneity might be real. That the universe may not experience time uniformly. That consciousness itself might be tangled with time in ways we are only beginning to comprehend. What follows is the story of what they never teach you in school about the hidden structure of time. A journey through the evidence, the theories, and the implications of time's true nature. It begins with a simple question that has haunted humanity since we first gazed at the stars and recognized patterns. What exactly is time, and why does it behave the way it does? The answer will change how you understand everything, from memory to mortality, from decision-making to destiny. In 1955, physicist Albert Einstein lay dying in a Princeton hospital. According to his biographer, his last written equations were an attempt to formulate what he called a unified field theory, a description of reality that would reconcile quantum mechanics with general relativity. The central obstacle? Time. Specifically, how time behaves differently at quantum scales versus cosmic ones. Einstein died before completing his work, but he left us with a profound insight. The distinction between past, present, and future, he wrote, is only a stubbornly persistent illusion. Was Einstein suggesting that our entire experience of temporal flow, the feeling that we move from past to future through the present moment, is fundamentally incorrect? And if so, what is the reality behind this illusion? To understand this question, we need to go back to basics, not to what we think we know about time, but to what we actually observe. When you look at your watch or phone, you are not measuring time directly. You are observing the movement of hands or the changing of digital numbers. Time itself remains invisible, untouchable. We measure it only through change, through motion, decay, transformation. This fundamental point was recognized as early as 400 BCE when Aristotle defined time as the number of movement in respect of before and after. But modern physics has revealed something startling about this change we use to mark time. It does not happen at the same rate everywhere. In 1971, physicists Joseph Haffel and Richard Keating placed atomic clocks on commercial airliners and flew them around the world, then compared them with reference clocks that remained at the U.S. Naval Observatory. The results confirmed Einstein's predictions. The airborne clocks recorded slightly different elapsed times than their earthbound counterparts. Time had passed at different rates depending on speed and gravitational field strength. This was not a measurement error. It was the first experimental proof that time is elastic, that it stretches and compresses depending on motion and gravity. Today, GPS satellites must constantly adjust for this time dilation, or they would lose accuracy by about 10 kilometers per day. What most people don't realize, explains theoretical physicist Megan Fitzgerald, is that these time differences aren't just theoretical. They're happening to you right now. Your head is aging very slightly faster than your feet because it's farther from Earth's gravitational center. Not enough to notice in a human lifetime, but absolutely real and measurable with precise instruments. And this leads us to our first revelation. Time is not absolute. There is no universal now that everyone experiences simultaneously. What you experience as the present moment is actually a localized phenomenon, specific to your position and motion through the universe. This realization shattered centuries of assumption. From Newton through the early 20th century, scientists believed time was like an invisible cosmic metronome, ticking at exactly the same rate throughout the universe. Einstein proved this wrong, showing that time is relative, woven into the fabric of space itself in what we now call spacetime. But relativity was just the beginning of time's mysteries. As we probe deeper into the quantum realm, things get even stranger. In quantum physics, particles can exist in multiple states simultaneously, a phenomenon called superposition. Only when measured do they collapse into a single definite state. This has profound implications for time. If a particle exists in multiple states until observed, then in some sense, its future remains genuinely undetermined until that observation occurs. This quantum indeterminacy led physicist John Wheeler to propose his famous delayed choice thought experiment in the 1980s. Wheeler suggested that the act of observation might retroactively determine whether a photon traveled as a wave or a particle, effectively allowing the present to influence the past. In 2007, researchers at France's Institut d'Optique confirmed aspects of Wheeler's proposal. They showed that measurements made on photons could indeed retroactively affect how those photons had previously behaved. The boundary between cause and effect, the very foundation of our understanding of time, was beginning to blur. But how can the future influence the past? This seems to violate our most basic understanding of causality, that causes must precede their effects. To make sense of these findings, physicists had to consider possibilities that would have seemed absurd a century ago. One such possibility is that time does not flow in just one direction. While we experience time as moving inexorably forward, the fundamental laws of physics work equally well in reverse. The equations that describe the motion of planets, the behavior of electromagnetic fields, even the quantum wave function, all remain valid if the direction of time is reversed. The asymmetry of time, the fact that eggs break but never unbreak, that coffee cools but never spontaneously heats up, this comes from probability and thermodynamics, not from any fundamental one-way property of time itself, explains theoretical physicist Benjamin Bryson. The laws of physics themselves are almost entirely time-symmetric. This symmetry suggests something profound. The arrow of time we experience might be an emergent property rather than a fundamental aspect of reality. And this brings us to a question that opens the next stage of our journey. If the laws of physics don't prefer one direction of time over another, why do we? The answer may lie not in physics alone, but in the relationship between physics, information, and consciousness itself. Consider an ordinary glass of water with an ice cube. Over time, the ice melts, and the water reaches a uniform temperature. The process never reverses. The uniformly cool water never spontaneously forms an ice cube. This irreversibility defines our sense of time's direction. But on a molecular level, each water molecule obeys time-reversible laws of physics. The irreversibility emerges only at the macroscopic level, as a statistical phenomenon involving countless molecules. It's tied to entropy, the tendency of organized systems to become disorganized over time. In the 1870s, physicist Ludwig Boltzmann formalized this connection between entropy and time's arrow. He showed that systems naturally evolve from less probable, more ordered states to more probable, less ordered states. The melting ice cube represents a shift from a less probable arrangement of water molecules to a more probable one. But here's where it gets fascinating. This entropic arrow of time is fundamentally about information. An ice cube in warm water contains more information than uniformly cool water because the molecules are arranged in a more specific way. As the ice melts, that information dissipates, becoming harder to track or recover. When we talk about entropy increasing, says information theorist Michael Reynolds, we're really talking about information being spread out so thinly that it becomes practically irrecoverable. The information isn't destroyed, that would violate quantum mechanics, but it becomes encrypted in such complex correlations between particles that we can no longer access it. This connection between time and information leads to a startling possibility. perhaps the one-way flow of time we experience isn't a physical law but an information processing limitation. Our brains and sensory systems can only process information in certain ways, creating an apparently fixed direction to time. In 2016, a controversial paper by theoretical physicists at the Perimeter Institute suggested that consciousness itself might be the source of time's apparent flow. They proposed that what we call now is actually the moment of information processing in conscious systems. A continuous creation of new information as sensory data is integrated into our mental model of reality. While still speculative, this theory aligns with emerging research in neuroscience about how our brains construct our experience of time. Research that reveals just how malleable our temporal perception really is. Neuroscientist David Eagleman has conducted remarkable experiments demonstrating that our perception of time can stretch or compress depending on circumstances. During intense fear, for example, time seems to slow down. This isn't because our brains suddenly process information faster, but because our amygdala, the brain's threat detection center, increases memory formation, creating more detailed memories that, in retrospect, make the experience seem longer. Your brain isn't a perfect clock, Eagleman explains. It's constantly recalibrating its time perception based on attention, emotion, and prediction. Time isn't flowing at a fixed rate in your conscious experience. It's being actively constructed moment by moment. This construction isn't just affected by emotion. Studies using brain imaging have shown that different neural networks process different aspects of time. The cerebellum handles precise timing for motor skills, while the basal ganglia and prefrontal cortex manage longer intervals. Damage to these areas can produce profound time perception disorders. Some patients with certain brain injuries report experiencing events in the wrong order or feeling that time has stopped entirely. Even more intriguing is how the brain sometimes reconstructs temporal sequences after the fact. In what neuroscientists call post-diction, our brains often determine the order of events retrospectively. In experiments, researchers can manipulate this process, making subjects perceive events in a different sequence than they actually occurred. Your sense that you're experiencing time flowing smoothly, moment by moment, is largely an illusion, says cognitive neuroscientist Melanie Fraser. In reality, your brain is collecting packets of sensory information across slightly different time frames, and then retroactively organizing them into a coherent narrative. You're constantly experiencing a reconstructed version of the past, not the actual present. This revelation that our experience of time is an active construction rather than passive perception forces us to reconsider what we mean when we talk about the flow of time. Is time actually flowing, or are we simply moving through it, creating the illusion of flow through our sequential processing of information? The evidence increasingly suggests the latter, and this brings us to a revolutionary concept first proposed by Hermann Minkowski in 1908 and later expanded by Einstein, the block universe. The block universe theory posits that past, present, and future all exist simultaneously in a four-dimensional block of spacetime. In this view, time does not flow. Rather, reality is a static, unchanging object that extends through time just as it extends through space. What we experience as now is merely our consciousness moving along this time dimension, like a spotlight illuminating different cross-sections of the block. It's helpful to think about a film reel, explains philosopher of physics Bradley Bennett. The entire movie exists at once on the strip of film, but when projected, we see only one frame at a time. Similarly, the block universe theory suggests all moments, past, present, and future, already exist. Our consciousness is just playing these moments in sequence. If the block universe theory is correct, then your birth, your death, and this very moment of reading these words all exist simultaneously in spacetime. The future is already there, fixed and determined, even though you haven't experienced it yet. This deterministic view seems to eliminate free will, which is perhaps why many find it uncomfortable. But recent developments in quantum mechanics suggest the block universe might be even stranger than originally conceived. Enter quantum mechanics and its most puzzling feature, non-locality. In quantum entanglement, particles can become correlated in such a way that the state of one particle instantly affects the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, appears to violate the speed of light as an information transfer limit. But what if entanglement isn't about information traveling faster than light, but about connections that exist outside our normal conception of spacetime? Physicist Hugh Everett III proposed a radical solution in 1957 called the many-worlds interpretation. He suggested that when quantum measurements are made, reality splits into multiple branches, each containing one possible outcome. Rather than a single block universe, we might exist in a vast multiverse of parallel realities. The math of quantum mechanics doesn't just allow for this possibility, it practically demands it, says quantum physicist Sarah Michaels. The wave function never actually collapses. It just appears to collapse from our perspective within a particular branch of reality. If Everett was right, then the hidden structure of time is far more complex than even relativity suggests. Time wouldn't just be relative. It would branch at every quantum interaction, creating countless parallel timelines, an ever-expanding tree of possible realities. But how could we ever test such a theory? Until recently, it seemed impossible. However, new experiments with quantum computers are beginning to probe the boundaries between these potential parallel realities. In 2019, physicists at the Federal University of ABC in Brazil conducted an experiment demonstrating what they called a quantum time flip. They showed that quantum particles can experience events in a superposition of different temporal orders, essentially experiencing two different sequences of events simultaneously. In one sequence, event A happens before event B, while in the superposed reality, B happens before A. We're not just talking about uncertainty in measurement, explains team leader Marco Caesar. We're talking about genuine temporal superposition, a breakdown in the very notion of before and after at the quantum level. These experiments suggest that time's linear structure might be an approximation that works at macroscopic scales but breaks down at the quantum level. And this brings us to the most mind-bending possibility of all, that time as we know it might be emergent rather than fundamental, a secondary phenomenon arising from more basic principles. Several leading theoretical physicists, including Carlo Rovelli and Fotini Marcopola, have developed timeless physics theories in which time is not a fundamental dimension, but emerges from quantum relationships between events. In these theories, the fundamental reality consists of a network of quantum events, and what we call time is simply a way of describing how these events relate to each other. Think about temperature, suggests Rovelli. Temperature isn't a fundamental property of particles. It emerges from their collective motion. Similarly, time might not be fundamental but rather a way of describing relationships between quantum events. This perspective aligns with recent developments in quantum gravity, the attempt to reconcile general relativity with quantum mechanics. Most quantum gravity theories, including loop quantum gravity and causal set theory, suggest that spacetime itself is not continuous but discrete at the smallest scales, composed of fundamental atoms of spacetime. If correct, these theories imply that time does not flow smoothly but advances in tiny, indivisible steps, quantum leaps from one state of the universe to another. At this fundamental level, the distinction between space and time might even disappear entirely. But if time isn't fundamental, why do we experience it so consistently? Why does it appear to flow in one direction? Why do we remember the past but not the future? The answer may lie in quantum decoherence, the process by which quantum systems lose their coherence through interaction with their environment, essentially transitioning from quantum to classical behavior. Physicist Brandon Marsh proposes that decoherence creates an apparent arrow of time by continuously producing new information as quantum possibilities resolve into definite outcomes. Each decoherence event is essentially irreversible, he explains. It creates information that wasn't there before, information about which quantum possibility actually materialized. This continual generation of new information defines the direction of time we experience. This information-based understanding of time connects physics with another field exploring time's hidden structure: complexity theory. Complexity theorists study how simple rules can generate complex, unpredictable systems, from weather patterns to stock markets to biological evolution. These complex systems exhibit what scientists call emergent behavior, properties and patterns that cannot be predicted simply by knowing the underlying rules. Consciousness itself may be such an emergent phenomenon, arising from the immense complexity of neural networks in our brains. What's particularly interesting is how complex systems create their own temporal structures. Consider biological organisms. Each develops according to its own internal rhythms: cellular division, metabolic cycles, circadian rhythms. These biological clocks often synchronize with external cycles like day/night patterns, but they represent autonomous temporal organizations. Living systems don't just exist in time. They create their own temporal structures, explains systems biologist Martha Fields. A cell dividing, a heart beating, a mind thinking, each generates its own patterns of change that constitute a kind of localized time. What we call biological aging isn't just passive existence in time. It's an active process of temporal self-organization. This perspective suggests that time isn't just a background dimension in which things happen. Rather, temporal patterns are actively constructed by physical processes, from quantum decoherence to neural firing to galactic rotation. And now we arrive at a truly revolutionary possibility, one that integrates these diverse perspectives on time's hidden structure. What physicist Lee Smolin calls temporal naturalism. Temporal naturalism proposes that the universe is fundamentally creative and evolutionary. Rather than existing as a static block or predetermined multiverse, reality is constantly creating genuinely new states, structures, and possibilities. Time, in this view, is the process of cosmic innovation, the continuous emergence of novel configurations from what came before. The universe isn't just being, it's becoming, Smolin argues. Time is real precisely because the future doesn't exist yet. It's being created, moment by moment, through physical processes that generate genuine novelty. This view reconnects physics with our lived experience of time as flowing and creative. It suggests that the future is neither fixed, as in the block universe, nor merely a branch in a predetermined multiverse. Instead, the future is truly open, being written through an ongoing process of cosmic evolution. But temporal naturalism raises a profound question. If the universe is constantly creating genuinely new states, what drives this creative process? Is there a deeper principle guiding cosmic evolution? Some theorists suggest information might be this guiding principle. Physicist Eric Verland has proposed that gravity itself might be an emergent force arising from the fundamental tendency of information to increase, a kind of entropic pressure toward greater complexity. Others, like theoretical physicist Bernard Blake, suggest consciousness might play a fundamental role. Consciousness might not just be a passive observer of time, he proposes. It might be an active participant in the creation of temporal structure, part of the process by which potential futures become actual presents. This brings us to a startling hypothesis, that consciousness and time are intimately connected not just subjectively, in our perception, but objectively, in the structure of reality itself. Evidence for this connection comes from quantum mechanics, particularly the measurement problem, the observation that quantum systems remain in superposition until measured by a conscious observer. While various interpretations of quantum mechanics attempt to remove consciousness from the equation, none have definitively resolved the measurement problem. What if consciousness isn't just observing time's flow but participating in its creation? Asks quantum theorist Maya Feldstein. What if the now we experience is actually the moment of reality's determination, the instant when quantum possibilities become definite actualities through conscious observation? This perspective aligns with the orchestrated objective reduction theory developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness arises from quantum processes in neural microtubules, and that these processes may connect our minds to the fundamental structure of spacetime itself. While still speculative, these theories suggest that our subjective experience of time might not be merely a psychological construction but a glimpse into time's actual nature, a window into the process by which reality continuously manifests from possibility to actuality. This brings us to perhaps the most profound implication of time's hidden structure, that our minds might exist in a more intimate relationship with cosmic temporal processes than we ever imagined. Consider memory. We typically think of memories as recordings of past events, stored in our brains like files in a computer. But neuroscience reveals that memories are not static recordings but active reconstructions, created anew each time we remember. When you recall a past event, your brain doesn't simply retrieve a complete memory. Instead, it reconstructs that memory from fragments, filling in gaps and sometimes incorporating new information. This is why memories can change over time and why eyewitness testimony is notoriously unreliable. Memory isn't about preserving the past exactly as it was, explains neuroscientist Brian Martinez. It's about constructing useful models of past experiences that help us navigate present challenges and anticipate future possibilities. This reconstructive nature of memory parallels how quantum mechanics describes reality, not as a collection of objects with definite properties, but as fields of possibility that become definite only when observed. Both memory and quantum reality involve a kind of retroactive determination, where the present actively shapes our understanding of the past. And this brings us to a revolutionary hypothesis about time's hidden structure, that past, present, and future might exist in a state of mutual creation, a dynamic interdependence where each influences the others in a complex feedback loop. Physicist Ruth Kastner has developed what she calls the transactional interpretation of quantum mechanics, which proposes that quantum events involve a handshake across time, a resonance between possibility waves emanating from both past and future. In this view, the present is created through a kind of negotiation between past conditions and future possibilities. We typically think causality only works in one direction, from past to future, Kastner explains. But quantum mechanics suggests a more subtle relationship, where potential future events can resonate back in time, influencing which possibilities become actualized in the present. If Kastner is right, then time has a hidden dialogue structure, a conversation between past and future that continuously creates the present. This would mean that the future, while not predetermined, can influence the present through the realm of quantum possibility. This perspective aligns with the growing recognition in both physics and neuroscience that prediction plays a fundamental role in how reality unfolds. Our brains don't just react to sensory input. They actively predict what will happen next and perceive reality through the lens of these predictions. Consciousness is fundamentally predictive, explains neuropsychologist Mark Anderson. Your brain is constantly generating models of the immediate future and comparing incoming sensory data against these predictions. What you actually experience is this predictive model, updated by sensory feedback. Similarly, quantum physics increasingly recognizes the role of probability and prediction in how reality manifests. Quantum fields describe potential future states and their probabilities, a kind of physical prediction of what might happen next. When measurement occurs, these probabilities resolve into definite outcomes. This parallel between neural prediction and quantum probability suggests a deeper connection between mind and matter than conventional science acknowledges, a connection mediated by time's hidden structure. And this brings us to the implications of time's hidden structure for human experience and meaning. If time is not simply a linear flow from past to future, but a complex, multidimensional process involving feedback between past, present, and future, a process in which consciousness actively participates, then many aspects of human experience take on new significance. Consider the phenomenon of intuition, those moments of insight that seem to arrive from nowhere, providing knowledge without conscious reasoning. If consciousness can access quantum fields of possibility, perhaps intuition represents a kind of temporal resonance, a sensitivity to future potentials resonating back into present awareness. Or consider creativity, the human capacity to bring genuinely new ideas, art, and innovations into being. If time itself is fundamentally creative, continuously generating novel structures and possibilities, then human creativity might be a localized expression of this cosmic creativity, a participation in the universe's ongoing self-creation. Even our sense of purpose and meaning might connect to time's hidden structure. If the future isn't simply predetermined but actively created through the choices we make in response to possibilities, then our actions have genuine significance in shaping what comes next. We aren't just passengers on time's arrow but participants in reality's unfolding. This perspective transforms how we understand our place in the cosmos. Rather than existing as temporary arrangements of atoms in an indifferent universe, we might be integral participants in reality's self-organization, conscious nodes in the network of cosmic becoming. The hidden structure of time suggests that consciousness isn't an accident or epiphenomenon, proposes philosopher of mind Melissa Franks. It might be central to how the universe creates itself across time, part of the process by which reality continuously emerges from possibility into actuality. This doesn't mean human consciousness controls reality or that we can change the past through wishful thinking. The constraints of physics still apply. But it does suggest that consciousness might be more fundamental to reality's temporal structure than conventional science recognizes. And this brings us to practical implications. If time has this hidden, participatory structure, how might we engage with it more consciously? Research on mindfulness meditation offers intriguing possibilities. Studies show that regular meditators develop enhanced awareness of the present moment and often report altered perceptions of time, experiencing it as more fluid and less rigidly sequential. Meditation practices from various traditions have long claimed to provide insight into time's true nature, notes consciousness researcher Benjamin Brooks. What's fascinating is that modern neuroscience is beginning to validate aspects of these claims, showing that meditative states involve altered activity in brain networks involved in temporal processing. Brain imaging studies show that during deep meditation, activity decreases in the default mode network, a brain system involved in self-referential thinking and mental time travel, remembering the past and imagining the future. This corresponds to meditators' reports of experiencing an expanded now that transcends ordinary temporal boundaries. Could these meditative states provide experiential access to aspects of time's hidden structure? Some researchers suggest they might, allowing practitioners to directly perceive the interdependence of past, present, and future, the dynamic, participatory nature of temporal reality. Similar altered temporal perceptions occur in various exceptional states, from flow states experienced by athletes and artists to psychedelic experiences to near-death experiences. All involve significant changes in how time is perceived, often described as transcending ordinary sequential time. These exceptional states might represent more than just subjective alterations in perception, suggests consciousness researcher Michelle Farrell. They might provide glimpses of time's actual structure, aspects normally filtered out by our everyday consciousness, which evolved to navigate the macroscopic, classical world. This perspective invites us to reconsider time not just intellectually but experientially, to explore how our conscious engagement with temporality shapes our lives and possibilities. If time is not just an external dimension but a participatory process in which consciousness plays an active role, then how we attend to time, how we remember, predict, and engage with the present, may influence not just our subjective experience but the actual unfolding of possibilities. This doesn't mean we can magically control reality through thought alone. But it does suggest that consciousness isn't just a passive observer of time's flow but an active participant in how temporal reality manifests. Consider the phenomenon of self-fulfilling prophecies, predictions that directly or indirectly cause themselves to become true. Research in psychology, sociology, and economics demonstrates that expectations about the future can significantly influence what actually occurs, from student performance to financial markets to international relations. Self-fulfilling prophecies aren't supernatural, explains social psychologist Brian Morgan. They're examples of how future-directed thought shapes present action in ways that make certain outcomes more likely. They're temporal feedback loops operating through conscious anticipation and response. These psychological feedback loops mirror the quantum temporal dialogues proposed by Kastner's transactional interpretation. Both involve resonance between future possibilities and present actualities, mediated by fields of probability. This parallel suggests that human consciousness might be participating in time's creative processes more directly than we realize, that our anticipation of future possibilities might actually influence which possibilities become actualized. Again, this doesn't mean we can control reality through thought alone or violate the laws of physics. But it does suggest that consciousness plays a more fundamental role in reality's temporal unfolding than conventional science acknowledges. And this brings us to what may be time's deepest mystery, its relationship to meaning and purpose. If time is not just a physical dimension but a creative process in which consciousness participates, then meaning isn't just something we project onto an indifferent universe. It might be intrinsic to how reality organizes itself across time, to how patterns of significance emerge from possibility into actuality. This perspective aligns with what philosopher Alfred North Whitehead called prehension, the idea that even basic physical events involve a kind of proto-experience, a sensitivity to past events and future possibilities. In Whitehead's process philosophy, the universe is fundamentally experiential and temporal, continually creating itself through the interplay of possibility and actuality. Meaning isn't just a human construct, suggests process philosopher Bruce Miller. It's embedded in the very structure of temporal becoming, in how patterns across time create significance and value. Human meaning-making is a complex expression of this more fundamental process. This doesn't reduce meaning to physics or elevate physics to metaphysics. Rather, it suggests that the gap between physical processes and meaningful experience might not be as absolute as conventional science assumes, that consciousness and meaning might be intrinsic to how reality creates itself across time. And this brings us to our final insight about time's hidden structure, that it might reconcile the scientific and experiential dimensions of temporal reality that have seemed so disconnected in modern thought. Since the scientific revolution, we've increasingly separated objective, physical time, measured by clocks and described by physics, from subjective experience time, the flow we feel, the meaning we create. This separation has left us with a fragmented understanding, precise mathematical descriptions of temporal processes divorced from the rich, meaningful temporality we actually live. The hidden structure of time suggested by contemporary physics, neuroscience, and complexity theory offers a path toward reintegration, a way of understanding time that embraces both its physical and experiential dimensions. If time is fundamentally participatory, involving feedback between past and future possibilities in which consciousness plays an active role, then our subjective experience of meaning and flow isn't opposed to physical temporality but intrinsic to it. This doesn't mean science should abandon objectivity or incorporate supernatural elements, but it does suggest that a complete understanding of time must account for consciousness not just as a product of temporal processes but as a participant in them, as part of how reality continuously creates itself across time. In this integrated view, physics describes the constraints and patterns of temporal becoming, while conscious experience represents direct participation in that becoming, not just observing time's flow but helping create it through attention, anticipation, and action. And this brings us back to Einstein's insight that the distinction between past, present, and future is a stubbornly persistent illusion. Perhaps what Einstein meant wasn't that time is unreal, but that our conventional understanding of it is incomplete, that behind the simple flow from past to future lies a far more complex and participatory reality. A reality in which time doesn't just pass but creates, in which consciousness doesn't just observe but participates, in which meaning isn't just projected but discovered through engagement with temporal processes that extend beyond individual human experience. This hidden structure of time invites us to reconsider our relationship with temporality, to move beyond passive subjection to time's passage toward active participation in its creative processes, to recognize that how we engage with past, present, and future, how we remember, attend, and anticipate, isn't just subjectively meaningful but might actually influence how possibilities become actualities. Not through magical thinking or violation of physical law, but through conscious participation in the quantum dialogue between possibility and actuality that physics increasingly suggests underlies temporal reality. This perspective doesn't solve all mysteries or eliminate uncertainty, but it does offer a more integrated understanding of time that honors both scientific insight and lived experience, that recognizes consciousness not as separate from temporal reality but as integral to its ongoing creation. And perhaps this is time's deepest secret, hidden in plain sight, that we are not just in time but of it, participants in the universe's continuous self-creation across past, present, and future. Not passive observers of time's flow but active contributors to reality's temporal becoming. The universe is not just a collection of objects moving through time but a process of temporal self-organization in which consciousness plays a fundamental role. Time doesn't just pass, it creates, and we are part of that creation. As we stand at the frontier of understanding time's hidden structure, we face not just scientific questions but existential ones. How shall we participate in time's creative processes? How shall we engage with past, present, and future in ways that contribute meaningfully to reality's becoming? These questions have no single answer but invite ongoing exploration, scientific, philosophical, and personal. They remind us that understanding time isn't just about solving equations or building better clocks, but about recognizing our place in the cosmic temporal order, as conscious participants in the universe's continuous self-creation. The hidden structure of time reveals not just how reality works but who we are within it, Not passive observers but active participants in the greatest creative process of all, the ongoing emergence of what is from what might be, across the vast sweep of cosmic temporality. What they never teach you about time in school is that you are not merely witnessing its passage but participating in its creation, a conscious agent in the universe's perpetual transformation of possibility into reality.